what is the impact of solvents in a reaction? Now, we're not necessarily used to thinking about what solvents are used for, but we actually intuitively use these in many different ways in our daily lives. Water is often called the universal solvent, and this is because of the wide range of different applications that we have for it. Right? We use it to contain a lot of food products, juices, milk even as a water-based solution. We also use it for cleaning, right? You can wash your hands with water, wash your clothes, all of those using water as the solvent. And a lot of times we have chemical reactions that are occurring in that water solvent as well as we carry out those various processes. However, we also use a variety of other solvents like acetone. Acetone is actually contained in most nail polish removers. So that acetone helps to dissolve and remove the nail polish that you might paint on your fingernails. And it's effective in that way, whereas water is completely ineffective at removing that nail polish. Now these differences here are mostly just based on solvent polarity. So our water is very polar. So we have our oxygen that's highly electronegative. It pulls electron density away from our hydrogens. There's a very large difference in electronegativity between our hydrogens and our oxygen. And so this creates a high degree of polarity for our water. So we say that our water is highly polar. When we compare this to our acetone, so acetone, of course, we have our oxygen that's bonded to our carbon. Oxygen is more electronegative than carbon, so it pulls that electron density toward itself. But the difference in electronegativity between carbon and oxygen is not as big as the difference between hydrogen and oxygen. Right? So electronegativity increases as we move to the right on the periodic table. Oxygen is on the far right side, carbon's in the middle, hydrogen is on the far left. Right? So we have moderate difference in electronegativity, very large difference in electronegativity. So that makes our acetone polar, but less polar than water. It also, of course, has these carbons down here at the end, and of course these carbons have the exact same electronegativity as our central carbon, so we have no dipoles down here to make our acetone slightly less polar as well. So our water then is very good at dissolving very polar things. Our acetone is not quite as good at dissolving highly polar things, but it can dissolve more nonpolar things, or things with lower polarity. So this, of course, follows our general rule of like dissolves like that you would have learned in general chemistry. So something that's highly polar like water tends to dissolve other things that are highly polar. Something that has moderate polarity like acetone will dissolve other things that are moderately polar. So how does this affect reactions? Well, a reaction will often occur in solution, right? So we need a way to mix our components together and have them in the same place for them to run into each other and react. So we often will mix our ingredients in some solvent for that reaction to occur. So if we look at a typical nucleophilic substitution reaction, so we might have an alcohol reacting with our hydrogen halide. So this is going to create our carbocation intermediate, which will then go to our final product. Now, of course, I'm not showing all the intermediate steps. I'm just showing that key carbocation intermediate that's from our rate limiting step. Now, the first thing that we need when we're carrying out a reaction in a solvent is we need, of course, both of our components to be able to mix and dissolve in that solvent. Right? So if we take this SN1 reaction, so we have an alcohol. Alcohols tend to be relatively soluble in water, as long as they're smaller alcohols. We have our hydrogen halide, which this is an acid. It's also going to be relatively soluble in water. So we could use water as a solvent here. because both of our two reactants would mix in that water. So that's our first requirement. Our solvent needs to dissolve our reactants. So we wouldn't want to use a very nonpolar solvent. So nonpolar solvents would be things like hexane or alkane-based solvents, because that very nonpolar solvent wouldn't dissolve our acid, which is going to be very polar, and our alcohol, which is also relatively polar. Now, as we saw from our earlier lecture, the main things that will affect our reaction rate is this rate-limiting step with our carbocation. Now, our carbocation, of course, was unstable because it has this positive charge and this low electron density. Anything that can share extra electrons with that will stabilize our carbocation and increase the reaction rate. Now, when we have our reaction occurring here in water, for example, our water, of course, as we see, has this sort of charge separation caused by our electronegativity. So if we take our carbocation and we put this in water, so our water molecules, they have their partial negative charges from their oxygens, and these partial negative charges can actually interact with our positive charge and can help to stabilize it. So that positively charged carbocation can get surrounded by partially negatively charged oxygens of our highly polar water molecule, and it can help to stabilize our carbocation. So polar solvents will stabilize our carbocation, and then anything again that stabilizes our carbocation will speed up our reaction. So we can say that polar solvents speed up our SN1 reaction. Now, the more polar our solvent is, the larger that partial negative charge will be, and the more it will be able to stabilize that carbocation. So increased polarity equals increased rate of SN1 reactions. Now let's consider the case of our SN2 reaction. So the SN2 reaction, of course, doesn't have that carbocation intermediate. So because of it, it's not quite as dependent on the polarity of the solvent. However, we do still often have a negatively charged nucleophile. And since we have a negative charge, we're generally going to need a highly polar solvent in order to dissolve that nucleophile and now allow it to react with our electrophile. So we still need a polar solvent. We also are going to need to consider something else about our solvent here as well. So in addition to being ranked as highly polar or less polar or nonpolar, we can also rank our solvents as being protic or aprotic. A protic solvent is anything that has hydrogens attached to electronegative atoms like oxygen or nitrogen. Right, so a protic solvent is a solvent that can form hydrogen bonds. An aprotic solvent would be something that doesn't have any hydrogens attached to electronegative atoms, and therefore it can't form hydrogen bonds with itself. We would also say that it's not a hydrogen bond donor. So a hydrogen bond donor is something that has a hydrogen attached to an electronegative atom that can be used to form that hydrogen bond. So we could also say that protic would be something that is a hydrogen bond donor. So if we look at our solvents up here, So our water has a hydrogen attached to an oxygen, so therefore it is protic. And our acetone, we have an oxygen here, but there's no hydrogens attached there. So this is aprotic. Now why do we care about protic or aprotic? Well, we care because if we have something that's protic, it's going to be forming hydrogen bonds, and our nucleophile is often going to be the target for those hydrogen bonds. Right? So in this case, our nucleophile is this hydroxide ion, and that negatively charged hydroxide ion is going to love to form hydrogen bonds with our nearby water molecules if we're doing this in our protic water solvent. So it's going to be forming lots of hydrogen bonds. And because it's busy forming all these hydrogen bonds, our nucleophile is actually going to get surrounded by water molecules, and it's going to make it hard for it to attack our alkyl halide here to make our products. Right? So you can actually get kind of this shell of solvent molecules around your nucleophile, blocking the attack of that nucleophile onto our alkyl halide. If we use an aprotic solvent instead, like acetone, so that acetone still has a partial positive charge that can be used to dissolve our nucleophile, but it's not going to be forming those hydrogen bonds to our nucleophile and creating the same strong interaction and surrounding of our nucleophile that the protic solvent does. So it makes it easier for our nucleophile to then come in and attack our electrophile and react to form our products. So our third key feature here, SN2 reactions prefer aprotic solvents. So overall, we can say something that's highly polar and protic, like water, works quite well for SN1 reactions. Right? We want something that's as polar as we can get, so it can stabilize that carbocation, as we discussed here in our second point. And generally things that are protic tend to be more polar. So we often see water or other alcohols that are also polar and protic as well. For SN2 reactions, we do still want it to be polar because we need to dissolve our nucleophile, but we generally want it to be aprotic so we don't get too strong of an interaction between our nucleophile and our solvent. So our SN2 reactions tend to prefer polar solvents that are also aprotic. Acetone is a very common solvent used for SN2 reactions. We also see other polar aprotic solvents like DMSO as well. And then in general, nonpolar reactions just aren't used for these substitution reactions, again because they're going to have a really hard time dissolving our reactants, as well as of course stabilizing that carbocation intermediate that we see in our SN1 reaction. So it turns out water and acetone, they're useful for dissolving different things in our daily lives. They're also useful for different reactions in our chemistry labs as well. Keeping track of what solvents we use and what the general properties of our solvents are, it's going to be very important whenever we're looking to decide what solvent we want to use for a particular reaction.